In this next section, we're going to start talking about a new shape called an ellipse. Today specifically, we're going to be focusing on several of its components and how to draw or recognize the graph. This information can be found in section 8.2 from your textbooks. This is not a slide that you need to copy down. Probably the only important thing on here would be the basic graph I have drawn and the definition that an ellipse is the set of all points whose distances from two fixed points have a constant sum. What I'm telling you is that if I pick any point on the ellipse and add up the length to each of the foci, then that combined length will be the same no matter which point I pick. So I could pick a point anywhere on the graph, and every single time if I add up the two lengths, the answer will be the same. So that's what creates this shape, an ellipse. What I have on here are a few applications for you guys. One application of an ellipse in life is to describe the path of an orbiting object. So when you're talking about something like the Earth orbiting around the Sun, it doesn't follow a perfect circular path. They follow an elliptical path. Another easy application to recognize is looking at a circle from an angle. So if you have any object, any kind of bottle or a cup even, if you, instead of looking straight down on the circular side of it, if you hold it at an angle, it's going to look like this elliptical shape. Similarly, if you have a cup full of a fluid, when you tilt the cup, the surface of the fluid is going to take an elliptical shape instead of having the perfectly round shape of the circle. And some more specific applications. One is used to break up kidney stones. They'll have a person stand at one of the focus locations, and then they'll have another object that emits waves at the other focus. And what happens is it vibrates, and the vibrations bounce off of the sides of the elliptical tank. And no matter which direction they go, they always happen to bounce right back to the other focus. So they're able to focus all of those vibrations onto the location of the kidney stone, which helps to break up the object. This is a similar idea to what you see with a whispering gallery, where if you have one person standing at one of the foci and another person standing at the other foci, then when they whisper, the sound, since it bounces off all the sides, everywhere it goes out, it bounces back to the second focus location. So it always comes back, and then that person will be able to hear you very clearly, even though people at other points along that path would not be able to hear you as well. So those are just some applications of an ellipse in case you were wondering, how is this ever used in life? So yes, we do have another list of equations. Again, personally, I don't like trying to memorize these in terms of the formula for the vertex or the focus. I'll show you on the next slide from looking at the graph how it makes a little more sense to look at these. However, it is important to recognize that a standard we use is the A value is greater than the B value is greater than 0. So by saying they're greater than 0, they both have to be positive numbers. And then I'm saying whatever two values you have underneath the fractions, I'm saying that A should be the bigger one. So when you see two different numbers like 9 and 4, then the 9 value is going to be tied to the A, and the 4 value is going to be tied to the B. You automatically make A the bigger one. So that's an important thing to keep in mind when you're doing these. Also, you'll notice that we do have two different forms of the equation. One is for when your ellipse is stretched more to the left and to the right, and the other one is for when it's stretched more up and down. So when it's stretching more left and right, it'll start with X. When it's stretching more up and down, it's going to start with the Y value. So one of the best things I can tell you guys to help you with understanding an ellipse is to break down what the H, K, A, and B values represent, because you can see all of those present in the equation. The H and the K values, just like with the last shapes we looked at, those are going to help you identify the center of your shape, just like with the circle. So we call the center of the ellipse H, K. So that's a point you want to be comfortable with identifying. The A and B values are a little bit trickier. So A is basically the long radius. If you have a regular circle, we know that the radius is the distance from the center to the side. But the problem is, with an ellipse, the distance isn't always the same. So what I'm telling you is that when we have an ellipse, in this case, I'm saying that the distance from the center the long way across will be the length A, and the short radius would be the length B. So that would be two things very important for you guys to include in your notes. A is the long radius, and B is the short radius. Now there's another value that you won't actually see in the equation, but this number will become very important for us, and that's the number c. So c is most commonly going to be found when you know a and b, you can plug them into the Pythagorean relation and solve for c. And the use of c is for finding the distance from the center to the foci. So c is going to be the distance to the foci. A and b will both be tied to finding the points on the sides on the ellipse themselves. And that's why major axis, so the reason that length is 2a is because when you're talking about the entire ellipse, it's the distance from one long end to the other long end. So that's why that whole length is 2a. And the same thing happens for the minor axis length. The short diameter, sort of, is 2b because you have one length of b going up, one short radius going up, and one short radius going down. So it's 2b's to go all the way across. It's like the diameter. So I think it's better to try and learn the meanings of A, B, and C from looking at the shapes. And whether you're doing a horizontal one or a vertical one doesn't matter much. So what's important is that you start off by finding the center of the shape. And then if you're taking that center and going all the way, the long way across the shape, that is a length of A. That's why when you look at the formulas here, it starts off at a center of H and it becomes a center of H plus A because it's added that A length all the way across. You can do the same thing with the short radius across the shape because if you take the distance the short way, that's the length B, and they don't have that point listed on here, but in this case, that would be the point H, comma, K plus B. Now, we're not often going to ask you for that one, but I think it does a good job of illustrating what we're doing here. We're saying go from the center and then go the short way across the shape. Basically, we're taking the center coordinate that we have, H, comma, K, and we're adding that length of B to the Y value. So you can do those same things vertically. It's not going to change much here. But I will show you that there's another point inside of the ellipse. That's the one that we call the focus. And so that length is the C value. So if you're going to the point inside the ellipse, that's like what the object is orbiting. If you're talking about a planet around the sun, for example, C is that distance. So those are the three important values, A, B, and C, kind of defined for you guys. They're all based on circling around the center HK. So there are three different types of examples we're going to look at. Now, this first one, you'll notice it's not actually in our standard form of an ellipse yet. And so that's something that you want to be able to recognize as we go along. If it's already in the ellipse form, great. Just go ahead and start identifying A, B, H, and K. But in cases like this, what I need to point out about the equation is that it's always set equal to 1. You might notice that it's always going to be equal to 1. So I'm saying if you don't have a 1 there, then there's something wrong, and you need to divide out some number somehow. So looking at our example, in this case, I need to divide everything by 36. That's what would make the other side of the equation equal 1. So I'm going to divide everything by 36 and see what happens. So now if I reduce those fractions, I'm going to have x squared over 9 plus y squared over 4. Let me try to redraw that 9. And that's going to equal 1. So this is where I can actually see that I have the standard form of an ellipse. If you already have something that looks like this, set equal to 1 with fractions under the x's and the y's, then you're ready and you don't have to worry about that step. So now that I've got my correct form, we should be able to start identifying things like the h and k values, which are both equal to 0 in this case, because I don't see anything being added to the x coordinate, and I don't see anything being added to the y coordinate. So those are both 0. Now we said A is always the bigger number in the bottom of the fraction, and B is always the smaller number in the bottom of the fraction. What's important is that A is always the bigger one. That's what we were going over earlier. A is always the bigger one. So the bigger number in this case is the 9 value, but it's the square root of that. So I'm going to say that A is equal to 3 and B is equal to 2. So try to make a habit of just starting off and listing those 4 important values. And a lot of times you're also going to have to go the next step and figure out the value C. So To solve for c, I'm going to have to subtract b squared from both of the equations. So I'm going to write a squared minus b squared equals c squared. So in this case, 9 minus 4 equals c squared. And then if I solve that equation, I'm going to get that c equals plus or minus square root of 5. Okay, so now let's actually answer what the question is asking us for. They want us to label the vertices, and the vertices are starting from the center of the shape, which is 0, 0. They didn't ask us for this, but it's helpful to list that out. And then we're going to stretch that coordinate in the x direction by 3. So my vertices, if I go 3 to the left and 3 to the right, because that's my a value, and it's underneath the x, so the number underneath x is 3, then 3 to the left would be negative 3, 0, and 3 to the right would be positive 3, 0. So those would be two of the endpoints of our ellipse. We could also do the short radius across, because I know that it's going to go up 2 and down 2, but usually they're just going to ask you for those vertices, the long stretch. And then the second piece of information we need is the location of the foci. Well, the foci are also going to be based on the center, starting from 0, 0, but we said the distance to the foci is the length of c. So my foci are going to be positive square root of 5 and negative. We'll just do both of them. Negative square root of 5, 0, and positive square root of 5, 0. So it's the same idea. It's going to go in the same direction as your major vertices. So since the vertices were going left and right, because that bigger number was underneath x, my foci are also going to go left and right, because the bigger number is underneath x. So those should always go in the same direction. If these are going in the x direction, then these should also go in the x direction. So now we have the coordinates of all of our vertices and foci. So now let's look at a couple graphing examples instead of algebra solving examples. So this one wants us to match which equation is shown in the graph. Well, let's start off by trying to figure out where the center of this ellipse is. It looks like it's gone to the right 1 and down maybe 2. So it looks like my center is 1, negative 2. Well, don't forget there's a sign change on the h and the k values. So this one's actually saying go left 1 and up 2, and that's not the direction of our ellipse. We want to go right 1 and down 2. So right now, I'm already pretty sure that this is the answer choice, but the other thing I want to show you is look at the distance from the center in the x direction. Since my bigger value, the value for a is going to be a 3 in this case, because a squared is 9. So that's telling me to go 3 in the x direction. So looking at my graph, it does appear to be going 3 to the right and 3 to the left for figuring out the stretch of the shape. And if I'm looking at the y piece, the number underneath y is a 1. The square root of that is still 1. So that's telling me up and down, my graph should be going a length of 1. So that one definitely seems to match. My answer choice would be that one. Okay, now let's also practice just trying to draw a sketch on our own, freehand. So you may be doing this with computer technology, but if you want to do this on paper, that's fine. So I'm going to draw a quick x and y axis here. And the first thing I want to plot is the location of the center. So my center is at positive 2, positive 1. Don't forget to change the signs. So positive 2, positive 1, that's the center of my ellipse. Now notice that in the y direction, the square root of 9 is 3. So in the y direction, my ellipse seems to be going up and down 3 units. So up 3 and down 3 from the center. Okay, well, how far does it go in the x direction? The number underneath x is a 4. So the square root of that is 2, which means my b value is 2. So in the x direction, I need to go left 2 and right 2 from the center. So with that rough sketch, you can just kind of trace through the dots that you've drawn. It's like we had a connect the dots outline. Now this isn't a very extreme ellipse, it's just slightly taller than it is wider. And that's what happens when your A and B values are kind of close. So that's all for the notes today. You should be able to do the assignment in class now. Thank you.